Good day, I'm Vincent Saxtetter, and this is the After the Age of Fire channel. This is episode 34, recorded March 7th, 2026. The title is Tuning and the True Price of Each Energy Source. This is a prepping channel, but it's not your average prepping channel. What I'm prepping you for is that you and your family line can flourish and thrive and reproduce in the new era that's beginning sometime around now. We are ending an era of multiplication, where every 22 years or so the human race was consuming about twice as much as it had been 22 years previously. So every generation had about twice as much as the previous generation. This is averaging over the entire world. So of course it went differently in the richer countries than in the poorer countries, but on average the consumption was multiplying by 2. And by now we consume about 46,000 calories of energy, of fuel, and of renewables. Most of that is fuel, coal, oil, and gas, and plus another 15,000 calories of food, fodder, and wood. That's per person per day. So since we each eat around 2,000 calories per person per day, that means that on average, the average human around the world is eating for 30. And we can expect that in the coming, so we've been assessing how much energy we'll have on hand per person per day after this era of multiplication ends, and the last 20 episodes or so have been devoted to looking at all the sources of energy, and the final conclusion is that after things settle out, sometime in the next 50 to 100 years, we'll be consuming about 30,000 calories per day, not the 46,000 plus 15,000. So we'll have a little less energy, but still far more energy per person than we had 300 years ago. But the biggest problem will be that we can't multiply our growth every 22 years, and so our feeling, at least right now, we feel like we're succeeding if we're growing, and if we're not growing, we're failing, and that will be a very traumatic adjustment to learn to live with and to thrive and in a situation where you can't multiply year on year. But there will still be ways to thrive, and that's what this channel is getting you ready for. And in particular, for many of us are not really reproducing very well and not setting up our families so that they would like to reproduce and that they'll have a way to adjust. And this channel is trying to give you ways that you and your family could adjust to the changes that are coming, and to the sources of energy that will be predominant. The main source of energy will be food from the land. So we've looked at coal, oil, and gas, and how much energy we'll have from those in the coming years. And we've also looked at food, fodder, and wood, our harvest from living crops. We just finished recently about 10 episodes on that, and then we've also looked at the renewables. So altogether, these three categories are all of the sources of energy that we have, the renewables, and the third one that I'm mentioning here is the renewables and nuclear. And I've argued already twice that the renewables and nuclear will never give us a combined total of more than 15,000 calories per person per day. There were two arguments. The first argument was the weakest. It was based on money and how much we're likely to be able to spend, how much money we can do without for building more wind turbines, solar panels, or nuclear reactors, and so it's based on that sort of argument. The second one had to do with us being matching well to the biosphere because we grew up in it, and the biosphere's way of providing energy, the ways that the renewables provide energy for us is much more awkward. We don't have electrical sockets in our bodies to feed off of electricity, for instance. And now I'm in the midst of the third argument. It started 2 episodes ago. This is the 3rd episode, and then there will be one more, which will tie it up. And it's based on, and this is the strongest argument of all. And basically what I'm trying to do is construct a pricing scheme telling you how you can tell which source of energy will cost the most, not just in money, but in terms of any sort of consequence for you and for the human race. And we'll find that the renewables are the most costly in terms of consequences, and that things like crops are the least costly. So if you want to get energy with the least hardship and the least work, then you'll be working on the land. So this argument is based on the notion of tuning. Tuning is my conflation of several concepts from math and from physics, like chaos and self-organized criticality. I've just explained it in the previous 2 episodes. And now I'm about to talk about consequences of tuning. The first is that everything we can do has everything that we do to get energy has consequences that are hard to tolerate. There's always some sacrifice you have to make to get energy, and for some kinds of energy you make a larger sacrifice, and then the second point is to give a kind of a pricing scheme, how large the sacrifice is going to be, and overall it's that we can the least sacrifices will be for are when we get our energy directly from the land, and then it's a larger sacrifice to get energy from coal, oil, and gas, and an even larger sacrifice when we get our energy from renewables. So that's the kind of argument I'm making, and so now I'll review just very briefly what tuning is, and then we'll start into the meat of today's arguments. So tuning, first of all, you can talk about a non-living system being tuned, like a snowpack on a mountain, or an earthquake fault system, or the weather, or a fluid in movement, or any number of almost everything you see around you is probably tuned. Then there's another level up of tuning, which is, and by the way, we know the most about the tuning of non-living systems, because you can analyze these things mathematically, and they're they're much more accessible to scientific analysis. The next level up is living organisms, and it's much harder to get at these mathematically because they're so intricate. But you can also talk about living systems being tuned, living organisms being tuned, a bacterium or a mammal, and then thirdly, another level up is you can talk about the biosphere being tuned. All 3 are tuned, but the relationship between one and the other is a relationship based on analogy. You can't carry on the math that you apply to non-living systems up to living organisms or to the biosphere. And the basic ingredients, the basic definition of tuning that I've offered has 2 points. One is that the tuned system is optimal. It's in some sense the best possible, or near the best possible, at doing some particular thing. Like, for instance, a snowpack, when it's tuned close to when it achieves full tuning, it's carrying the maximum possible weight that it could on that particular mountain on that particular day. But also by that by the same, because it is tuned, it also, this is the second point, its behavior depends crucially on the behavior of every little detail of the snow and everything inside the snowpack, which means that it's very close to avalanche. You just poke it in the right place and it'll all fall down. So it's doing its best possible job of carrying snow, but it's also sensitive to every detail of its makeup. Same thing with the weather. Airflow sets itself whenever the air flows past an obstacle, and you'll notice a lot of obstacles on the ground blocking the air. Whenever it flows past these obstacles, it tunes itself to exert the maximum possible drag or force on that obstacle. It arranges itself in vortices, something like tornadoes. We usually don't see them because the air is transparent, but there's an awful lot of them around us whenever we or something else moves or the air moves past us. And so it's doing its best possible job of pushing things. But by the same token, it's also dependent on every single detail of what's going on. So we have what's called the butterfly effect, so that you cough now and that might be the cause of a typhoon turning north instead of south a month from now. So that's my very brief review of what tuning is, and now we'll get into the meat of today's arguments, which is I'll start by talking about how every tune system can be poisoned, and I don't mean poison in the sense of doing evil. I mean that what I mean is that every tune system can be interfered with in some subtle and seemingly innocent ways that result in an apparently miraculous failure. So this is a lot like what I was saying about the butterfly effect, that there's some, whenever you find a tuned system, there's some point you can press on it that looks perfectly innocent and will have a huge effect. So, for example, I just talked about changing the direction of a typhoon, but also you can do, many times people have succeeded in doing cloud seeding. That means you do something to the air. Maybe you take an airplane up and you dump some crystals of something into the air, or maybe you shine lasers on the air in some particular place, and suddenly it rains, just because you did, obviously because you did that. You might get tremendous amounts of rain, like even in deserts, like around Dubai. You can get a huge rainstorm all of a sudden by cloud seeding. Okay, the problem is that you don't know when and where to do the seeding. It happens sometimes and in some places, but you don't know quite how, in any particular situation, how it's a luck of the draw. Okay, so but it's indisputable that you can get water out of the air on occasion by seeding it. Just as on occasion you can change the weather. Or another example that I was already discussing is, on occasion, by stepping on a snowpack, you can cause an avalanche. Or even just dropping a pebble someplace could cause an avalanche. So that's an example of what I'm calling poisoning. You do something very small and you get a huge effect. And every tune system has this property that you do something. It doesn't say I'm not saying every small thing that you do to a tune system will cause a large effect, but some small thing may cause a large effect. Another example is fault systems for earthquake faults. And I want to give a particular example of an earthquake which humans caused, and we know exactly how we did it, and we know that we got a much larger effect than you should expect, because in fact we've caused thousands and thousands of earthquakes, probably hundreds of thousands by now. Whenever you drill into the ground and you inject water, the the water takes up space, of course, and the rock around it has to adjust to the water's presence, and it adjusts more or less like a spring. And it stores energy as you're pumping the water down, and that sooner or later the rock may spring back. When it springs back, it will release an amount of energy that is connected to the amount of water that you pumped in. If you pump in 1 ton of water, you'll get a certain amount of energy out of the earthquake. If you pump in 1,000 tons, you'll get 1,000 times more energy out of the earthquake that results when the rock springs back. So we've done a lot of pumping, especially in this era of fracking, and so we've seen a lot of earthquakes. Okay, but there's one particular earthquake that stands out that we know we made, and that is far larger than you'd expect based on the amount of water pumped in. So in the city, it's a city on the coast. It's a very large city of several 100,000 people. It's on the eastern coast of South Korea. It's named Pohang. It's an industrial city founded to make steel. And on November 17th, 2017, there was an earthquake. And this earthquake, we know exactly why it happened. It's because there was a geothermal project 2 kilometers north of Pohang, and that geothermal project injected water to a 5-kilometer depth in hopes of later the water would warm up and then they would pump it out again. So they injected about 3 Olympic-sized swimming pools underground at 5 kilometers, and based on the physics of rocks and how they spring back, the magnitude of the resulting earthquake should have been a 3.0. It should have been barely noticeable to anyone around. Instead, that earthquake was 1,000 times stronger than you'd expect based on 3 Olympic-sized swimming pools. It was a magnitude 5.4, and it rocked the entire city. And I was there, and it really, there was also an aftershock, and the 2 earthquakes together really rattled me. There were about 90 people who were injured in that earthquake. There were many buildings that were damaged, and at the same depth where the water was injected, 5 kilometers deep, there was a plate of stone about 5 kilometers long and 1.6 kilometers wide that moved 1 meter. That was the actual ground movement that caused this earthquake. It moved 1 meter southwest, and it moved 5 centimeters upwards. Okay, it was a huge thing altogether in return for 3 Olympic-sized swimming pools of water. Okay, and the reason was that these guys who did the geothermal project injected the water right into a fault zone that had a lot of clay in it, which makes water movement even harder underground, increases the pressures. So what they had was a tune system, and they played with this tune system, and they got a large result. That's what I call poisoning. A very large result, 1,000 times larger than they should have gotten. And the reason why I'm concentrating on this earthquake is not just because I was there. It's because it is as far as I know, it's the only instance where we know very well that we did it, and it was a poisoning event. It was an event where we got far larger energy, far more energy out of it than one would expect based on the amount of water. Okay. Another example, very important example of poisoning is the structural collapse of aged structures, like bridges, and I'll talk about a bridge in a minute, or of aged people. So anything that's under stress, wear and tear for a length of time, and will eventually become tuned. So let's talk about a bridge first. It become tuned and therefore vulnerable to to very small things. So there have been many bridges and many other man-made structures that have collapsed over the centuries, but I'll talk about one. One is the Ponte Morandi Bridge in Genoa, which collapsed on a morning in August 2018. It was 51 years old. It looked good. It was carrying large amounts of traffic up until the last moment, including lots of semis or lorries, lots of heavy things, and it looked strong. It was strong. It was a strong bridge. It was carrying, it's more or less the highway running. It was a highway running across this bridge. This wasn't a small bridge. It was a pretty huge thing, and it looked good. Maybe the design wasn't the best. It was designed with large external steel cables, and those cables rusted, and by the time of the bridge's collapse, they had lost 10 or 20% of their weight to rust, which wasn't a good thing. But still, it was strong. It was doing its job until the last second, and then suddenly it collapsed. And we'll never know why it collapsed. It was some very small thing, small enough that we can't tell what it was, and never will be able to tell what it was. Some people think maybe it was a lightning stroke, but how a lightning stroke would cause a strong bridge to collapse, I have no idea. But anyway, it just was there, and then it wasn't. And it's the same thing with people, aged people. You can have somebody who's strong, who's still very capable, very active, very intelligent, and close to the peak of their abilities, and then suddenly something very small happens and they're dead. Or somebody who's maybe a bit past their peak, maybe by now they're on 15 or 20 medications, but they still have an active social life. They spend 6 or 10 hours outside of the home every day, maybe in retirement, or maybe carrying on their job, and something small happens and they're dead. And there's no predicting somebody may live through. This person maybe have already been living with cancer for 20 years, or diabetes for 30, or they may have been through all sorts of risks and hardships, but something very small like a fall in a bathtub may be the end. So it's very hard to tell what a particular aged person is vulnerable to and what they can withstand, but there's no doubt that aged people get to a point where something very small, we don't know which one for which person, will kill them. And these are one-off vulnerabilities. One person's weak spot may be different than another person's, but there's no doubt that sooner or later we all develop weak spots, and sooner or later all of us die of them. So for tune systems, certainly there are things that I'm talking about, things that wouldn't kill the same person when they were 30 or 40, very small things, and when they're 70 or 90, it's a near thing, or it's death. This is what I mean by poison. You have you do something small to a tune system, and there's a large result. And for aged structures and aged people, it can be complete collapse. And it's one-off. The weather today, if I want to do cloud seeding today, I would have to do it in a different way and in a different place than if I wanted to do cloud seeding tomorrow. Or a different aged person will be one aged person may be vulnerable to one thing, and another person may not be vulnerable to that, but vulnerable to something else. A fault system, we've drilled probably 100,000 or more and pumped water into many places, um, and only the one drilling effort in Pohang rewarded us with this poisoning event. So it's unpredictable when and where you can poison an earthquake fault. Okay, so that's it for non-living systems. Well, I think the aged person, sure, those are living systems, but the crucial failure mode of an aged person is just like that of 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 any old structure. So I lump them, that sort of of failure, the sort of one-off failure of human bodies is a lot like the one-off failures of structures. So anyway, I class those all as the non-living systems for the moment, and then let's move on to living systems. Okay, and they're tuned like the non-living systems, but somehow more so. And the distinguishing thing as far as poisoning goes for living systems is that we have poisons that are serial killers. So, because, in other words, if a virus could kill 100 million people, um, because they're living, you won't find, you can't do the same identical cloud seeding 100 million times and get 100 million deluges. But you can do something very similar. You can do exactly like that with humans. You can kill humans or people or humans or animals or crops off by the millions by using the right poison. We have serial killer poisons, and it's specifically because when you see the same poison destroying many tuned systems, it's because you know that those tuned systems must be alive. And the reason is that we share our vulnerabilities. Children share their identity with their parents and with other species. So because of all the things we have in common with our parents and with many other people and even with other species, we're vulnerable to many of the same things that they are. And also we're super tuned. We're somehow more tuned than any non-living system. That organisms somehow fit together and work more beautifully and more. You know, it's more than any fault zone or set of or weather system. So some examples of this kind of tuning where a small thing can have huge effects is the way that a baby inside a mother's womb can be affected by her mood. And we'll certainly, in fact, we are affected by our mother's moods in the womb, and then and those effects continue to color our experience and our perception of everything and our responses to everything throughout the rest of our lives. And it's just an elephant in the room, and also actually we begin to learn language already inside the womb. Inside the womb, we can already learn. In fact, babies already are learning what are syllables and how words are broken up into syllables, and they're starting to learn what their own language, the language of their mother, sounds like. They can distinguish between mother's language and other languages already inside the womb. And that's crucial for what happens afterwards. Okay. Another example is magicians' tricks. Magicians have ways of fooling your eyes or your brain to make it seem like your watch just disappeared or some money just appeared or all sorts of other things. They have tricks. Those tricks are exploiting vulnerabilities of your mind and your eyes and your body. There's also viruses, which I just mentioned, and then actually all through our daily life, much of what we do is we exploit the vulnerabilities of the living things around us. It makes a lot of the drama and the interest of human life. and actually of everything that happens in this biosphere, the continual competition and play between different organisms. So, so that's the key, the main that's the key difference I see between poisoning and organisms and poisoning and non-living systems. It's organisms share vulnerabilities, and therefore you have these serial killer poisons. With non-living systems, they're not. When you do find a poison, it's not repeatable. You break one thing, and you can't. It doesn't. The magic thing that takes down an avalanche on this mountain on this day is not going to be the magic spot that takes down an avalanche on another mountain, or even on this mountain on another day. So then one step up we went from non-living systems to organisms, and then poisoning in the biosphere. What about poisoning the biosphere? Well, first of all, the biosphere doesn't have DNA. It's not clearly alive. If you want to say it's alive, that seems to me like more of a theological statement than a scientific statement, because clearly if it is alive, the way it's alive is much different than the way that the organisms on this planet are alive. And there's no known, our biosphere has no known siblings or parents. If you could point to another biosphere and say this is clearly a sibling of the Earth's biosphere, that would be one thing, but until now we have no evidence of anything like that. So we can't expect any serial killer poisons to apply to this biosphere. Nonetheless, it is a tuned system, and because our biosphere is a tuned system, every one of our actions interferes with the biosphere. And in general, because the biosphere is tuned to do close to the best possible job of taking care of the needs of its member organisms, everything that we do here, in general and as a rule, reduces the biosphere's harvest, and it reduces its ability to provide for our needs. So everything we do here on this biosphere has consequences, and because the biosphere is very close to being in an optimal state, maybe it is optimal, I don't know, doing an optimal job of providing for our needs and for those of many other organisms, and therefore when we change something, the likelihood is that things are going to get harder for us. And because it's a tuned system, a small change, an innocent change that we make, will usually have a much larger effect than we would expect. And in fact, we generally don't foresee most of the consequences of our actions, and oftentimes we don't even notice them after the fact. I just want to point out something. When I say poisoning, and I think I already said this, I don't mean that it's necessarily evil. When I say poisoning the biosphere, or poisoning an organism, I don't mean that it's necessarily an evil thing to do. It just means what I'm saying, but what I mean by the word poisoning is that you get a much larger effect than one would expect, and the reason why that large effect is so large is because the system was tuned. I want to talk again a little bit about whether we could kill the biosphere, which seems to be in the news a lot about how we could really damage the biosphere, or maybe end life on this planet, or somewhere close to that. I don't think this is any real possibility. Okay, what we should worry about is not what we're going to do to the biosphere, but how what we do will affect us. How when we poison the biosphere, when we make unexpectedly large changes to the biosphere, how will that affect us? That's what we should be more worried about. Because why do I think we shouldn't have to worry? We shouldn't worry that much about the biosphere. The reason is that for any tuned system, it's very hard to figure out ahead of time what the poisons are for that particular system. It's like finding, it's like you have to find the right key, and it could be any of a million keys, and you have to find the right one. So you could spend all day looking for the right key to destroy this particular fault system, or find the right precise point to pound on the Ponte Morandi bridge. And in fact, in some sense, things were pounding on the Ponte Morandi bridge for 51 years before finally the right key fit and it collapsed. You could spend a long time doing it. Say, like, I think Fleming found the first antibiotic, and for the next 20 years we kept finding antibiotics that were very helpful. But for the last 50 or 60 years, we keep looking for antibiotics, spending billions of dollars, hundreds of billions probably by now, trying to look for antibiotics. And for 50 or 60 years, we've essentially made no progress. It's really hard to find these secret keys to bacteria that will poison bacteria. We had some good luck at the beginning, but now it seems to be done. And so what I'm saying is, you have to look for any tune system. You have to look and look and look and look, and have a lot of very good luck before you find the key that brings it down. Okay, and our biosphere is a tune system, so you'd have to try really hard, looking and looking and looking, before you'd find that secret poison that will have a large effect. So I don't see how we're likely to find that in the next few centuries. So I think that our ideas and our fears for destroying the biosphere are probably very far off the mark. You know, we have these really absurdly simple ideas about you change one variable, and suddenly everything goes wrong, and we think of some variable that seems especially significant to us, and if you change that one variable, well then catastrophe could happen any time now. You know, the world could turn into a ball of ice, I don't know. And the thing is, you know, the biosphere has been through a lot worse than anything that we can do right now. For instance, the carbon dioxide that we're adding to the air. The biosphere has been through much larger changes in the amount of carbon dioxide in the air, and all sorts of things have continued to live through that. There have been huge eruptions that covered, you know, large fractions of a continent with lava, and we can't match that sort of thing. There have been meteorites, huge ones, that we can't match the effect of a meteorite. The things we can do to this planet are relatively small compared to the changes and catastrophes that's been through, and even in the last few million years. So animals like us, or perhaps they are us, humans, started walking around this earth 3 million years ago, and since then there have been a lot of these what are called ice ages. What the real scientific name is glacial maxima, where a large amount of the earth was covered with ice, and the geography changed a lot, the weather changed a lot, and we lived through those. We haven't seen anything like that yet, that was caused by us. And so I think the changes that we make are fairly small, and compared to the changes that the biosphere has been through, and also it's sure I expect that there are poisons that can cause huge effects in the biosphere, but I don't expect us to find them overnight, or even in a century or two. It takes us just to find the poisons that will bring bacteria down. We can go for 50 years without finding much, and we know what it's like to try to find the secret poison that affects a strong building. You know, you have to do a lot of pounding and a lot of checking and before you find the secret thing that finally brings the thing down, or else you can just go at it with a sledgehammer and or a large piece of machinery and just smash it. That's what we usually do. But that's different from finding its poison. So I went through all this to talk about the poisons that the biosphere, first of all, that non-living things are vulnerable to, then what organisms are vulnerable to, and finally the biosphere. And the whole point of this is to finally arrive at a way of pricing, of determining the real price of each energy source. So, and here's the key thing. Okay, so every change we make to this biosphere, it is a tuned biosphere. It has a larger effect than one would expect. Everything has, and they keep. In fact, it may take you a while even to notice the effects, but we pay a price for everything we do, and therefore we need to think about the price of our energy sources, and we have to think about which energy sources have larger effects and therefore have a larger price for us. And the key is the energy sources that are weakest poisons are the ones that we can get the most energy from. So, for instance, if you had one way of getting energy that caused a ton of smoke to come in to be emitted into the air for every unit of energy, and you had another way of producing energy that would produce 10 tons of smoke, so A produces 1 ton and B produces 10 tons, then you can get more energy from A, okay, from the one that produces 1 ton of smoke per unit of energy, because, well, either you could produce 10 times more energy and get the same amount of smoke and have the same health effects, okay, or you could produce maybe just 3 times more energy and you would have less health effects and you would have more energy. So you have to think about the effects, the side effects of producing the energy. The one that produces the greater side effects, the stronger side effects, and more of them, that's the one that will give you less energy. So, and the way to determine which energy source has larger side effects, has a larger poisoning effect, is it's the one that's further away from the biosphere's natural way of doing things. So energy sources that are closer, that keep the biosphere and us closer to how things were before we interfered, those are the ones that are least poisonous and that can give us more energy. So I'm saying energy source that is closer to the way the biosphere was before we started really interfering 300 years ago is also the one that has the least poisons, the least poisoning effect, and the one that will give us more energy. So let's talk about the biosphere's way of doing things. Very briefly, its way of delivering energy is by storing it in carbohydrates and sugar and proteins and in oil. Okay, and then those were available for hunter-gatherers to eat. So our natural way of getting energy from the biosphere is by wandering around, searching around for berries and nuts and grains and things like that, things that we could eat, and by hunting animals. That's the natural way of doing things. That's what we're designed for. We're designed to be on 2 feet, walking around the landscape, looking at everything, and searching for things that we could eat. And alongside that, the biosphere also delivers us wood and straw and dirt and rock to take care of other needs. So it's not just things we can eat, but it's a variety of other needs like housing and places to stay, water, and clothing. So that's the biosphere's way of relating to us, and that's the least poison. That's like I'll say that's zero poisonousness. If we could live like hunter gatherers, there would be. I mean, the only side effect would be if there were. No, I mean that's just the natural way that we're bred, and that the biosphere is adjusted to for us to live here and to get what we need from the biosphere. Okay, and then there are 3 degrees of separation that I want to discuss that from the biosphere, that 3 steps away from the biosphere that we've taken. And as you go further and further along these 3 steps, these 3 steps become progressively more poisonous, and therefore we can get, in the end, we'll find that the side effects are so large that we'll get less and less energy from them. So the first step away from the biosphere was to stop hunting and gathering and start farming and pasturing. Okay. Now it's true that by hunting and pasturing we were able to get more calories and feed more people, but there was a price for it, which I'll come to very shortly. Okay. But that's the least poisonous of the steps. Then the next step away is coal, oil, and gas, and I'll talk about that at some length in this episode, and that's a step further away from the biosphere. It's not, and it has a bigger price. It's more poisonous. And then the third step away is the kind of energy that's based on electricity. So the renewables in particular, they basically only generate electricity. That's the only use we have for them. Or if you use coal only to produce electricity, not for heating and not for powering machines, or oil or gas, that is also in the same realm as the renewables. And electricity is a jump beyond. It's far less like the biosphere than coal, oil, and gas are. And therefore, that's the ultimate reason why we will find that the renewables have such large consequences for us individually and as a race that we won't be able to tolerate that much energy. We won't be able to tolerate more than 15,000 calories per person per day. They're far, and I'll be talking about the consequences of using electricity-based energy sources in the next episode. So I'm not against any of these energy sources. I'm not against the renewables. I'm not against coal, oil, and gas, and I'm not against farming or pasturing. Okay, I'm just saying we need to choose carefully when we choose an energy source. Think about how poisonous it's going to be, and use less of the ones that are more poisonous. So you just, you pick your poison. You just think, okay, well, if I use this one, I'll have consequences in my life that are 5 times worse than if I use this other one. So maybe I should use a little less of the more poisonous one. So the first step away from the biosphere's way of doing things, the first step away from hunters and gatherers, is the move on to farms and pastures. And that may seem fairly innocent and idyllic, but it already had some large consequences, very large ones. And in the previous episodes on our harvest from the world's plants, I spent some time discussing the effects of our actions and our farming in particular on the world's land, and how our farming practices tend to destroy the world's land. And so I'm not going to go over those again. I went on over those at some length fairly recently. You can back up a few episodes and look for that. I forgot which episode it was. Let's see. I think one of the episodes was episode probably 29 and 30, probably those two episodes. Yeah, 29 and 30. You look at those. But I'm not going to dwell on our effects on the land, but I do want to talk about briefly the effects of farming and pasturing on us. First of all, we are hunter-gatherers, and that means we're naturally built to be omnivores. We eat everything, okay, and that's our healthiest way of living, is to have a lot of species in our diet. And on a farmer's diet, we eat less species, and they're less fresh, and we get less nutrients from them. It's hard to overstate. I mean, I just said that very quickly, but it's huge, okay? And then we've moved away from the fats and proteins and vegetables and fruits that were important parts of our diet, and now most of the calories in our diets come from refined carbohydrates, from grains and flours and potatoes. So, and as a direct consequence of our living on carbohydrates mostly, sugars also, we have a worldwide epidemic of obesity and diabetes and heart disease, because it's huge. Everyone knows knows the effects of heart disease and diabetes. And anybody in a rich country knows about the effects of obesity on many of the people around them. We know it's killing a large fraction of our deaths are caused by these sources. Okay, and that's a direct consequence of our move into farming. And I mean, there are other things combined, like there's also once much of the population moves out of the farms and is sitting in office buildings and homes and cities, it makes it that much worse. But the farming, moving off of a hunter-gatherer diet, is absolutely essential to producing these modern epidemics. Also, living on carbohydrates really changes our brain chemistry and our moods, our ability to think, and our ability to exercise self-control. And this is being made obvious right now by many people's experiences, and it's being seen in scientific studies, lots of them, that often, not everyone, but many of the people who go on certain diets find huge changes in their self-control or their emotions. Sometimes even if they have mental diseases, the mental diseases go away. If they go onto a diet that has no sugar, or maybe a diet that has no refined carbohydrates, no flour, or maybe even a keto diet, a medical keto. There are many keto diets. I'm talking about a medical keto diet, which is one where you ensure that 10% of your calories come from proteins and carbs, and 90% of your calories come from oils and fats. So it's a very, very fatty diet, and it really changes your body chemistry and especially your brain chemistry. And so on this kind of medical keto diet, somebody who has untreatable, uncontrollable seizures may stop having them within a few days, or somebody who has schizophrenia may find that the hallucinations go away, or somebody with depression may find the depression goes away. And so it's huge, and the fact is that many of the mental diseases and many of the emotional problems that we have would be not for everybody, but for a good fraction of our population, just wouldn't be there if we were on different diets that were closer to that of a hunter-gatherer. Okay, there's also, so that's the effect of food, the farming lifestyle's food. That's its effect, and it's huge. Okay, then also our posture. We were standing up, walking the world, and looking the world in the eye, and now when we're working the land, if we're walking around on the land weeding or whatever, we tend to be bent forward or crouching while we're working the land. It's not a natural posture not a healthy posture. And then even less healthy is that when we're not working the land, we tend to be sitting or slumping, which is just not the way we were built. We weren't built for this posture, and it also has effects on us. And then one more kind of side effect of living, of being in a farming or pasturing, is that we were on the move, right? And we were constantly watching. We had to keep our eyes open for predators, but also for food and for all the other things we were getting from the land. And the landscape was always changing. The weather came and went, and you could see the weather move across the landscape, and it had direct consequences for us. You could see the animals moving across the landscape, again with direct consequences to us. And we're designed to notice everything that moves. For good reason. It's hard to keep our eyes off of anything that moves. But now we live in farms where the farms grow slowly and not much is changing on the field. It looks pretty much the same day to day. And or we are inside of buildings, inside of rooms where really nothing is moving. Our furniture just stays where it is. And it's unchanging, and it may stay in exactly the same place for 50 years. And because of this is not the kind of environment that our nervous system and our soul and our psyche were built for. And because of this, we begin to be a bit dulled, and we lose vigor and a little bit sleepy in a certain sense. And actually it makes us ripe for any sort of excitement, and in particular for anything that moves. We can't keep our eyes off of the TV or the cell phone, and we're vulnerable to addictions, and a lot of that, it's not the only reason why somebody might choose an addiction, or get into an addiction, but one of them is just that we aren't engaged in the same way that we were when we were walking the land, the African savanna. So these are farming and pasturing may seem idyllic or ideal, but already, because they're a step away from hunting and gathering, we have side effects, and they're rather large. Okay, but there's a second step. It's the move to coal, oil, and gas. Okay, and I'll talk about how they're the distance between them and hunting and gathering, and when you think about the distance, whether they're like or unlike, you should think that to the degree that coal, oil, and gas are like the usual way that the human race lived with until very recently, that to that degree they'll be less poisonous and we can get more energy from them, and to the extent that they're further away, they'll be more poisonous and we can get less energy. And overall, we'll find that the differences between coal, oil, and gas are a lot more different from the life of a hunter-gatherer than farming and pasturing are. So I'll talk about 4 different categories, and that'll be the rest of this episode. And then in the next episode, I'll take up the renewables and talk about and the next episode will be about the renewables and their price, how poisonous they are. We'll find that those are even less like the natural way of doing things than coal, oil, and gas. That's why we won't be able to stand building too many of them. So coal, oil, and gas, the fundamental reason why they're close, still fairly close to the hunter-gatherer way of life, is that they're produced by the biosphere. There's some debate a little bit, but the bulk of almost all of the coal, oil, and gas, if not all of it that we're using, comes from dead plants. So that's the key why we're able to use so much of them. Okay. On the other hand, they've been underground under high pressure and often at high temperatures for millions of years, and by now they've been chemically transformed so deeply and so radically that nothing can eat them. So they've crossed a divide that they're still somehow connected to the biosphere, but they've crossed a divide so deep that the biosphere just can't eat them. So yeah. So I'll talk about 4 levels of likeness, four levels of similarity between coal, oil, and gas, and the natural way of doing things, the way we were as hunter-gatherers. So the first level is like, so coal, oil, and gas being like that, then somewhat like, then a little like, and then unlike. So there's only one thing that I can think of that's like our way of getting energy from living plants. It's that the energy content of coal, oil, and gas is similar to the energy content of dry plant matter. So coal is about the same on an amount of energy per weight as dry plant matter, and oil and gas are about twice, a little more than twice, which is I mean, it's a lot better than batteries. Batteries are 1/20th or something. So it's in the same ballpark, which means that coal, oil, and gas are portable. We can take them with us. Now, natural gas is very inconvenient, okay, to carry with you, but you can move it around in ships or in pipes. Well, that's natural gas, and coal and oil you just can carry with you. You can power cars and ships and things that way, and that's hugely convenient, and it's basically because they retain enough of the same chemistry as with dry plant material that they can store an amount of energy that's similar. And when I was saying that oil and gas hold a little more than twice, I'm comparing that to dry protein or carbohydrates. Now, vegetable oil contains twice that, so natural gas and gasoline are almost the same as vegetable oil. Another, I guess, one more thing that's like is that the coal, oil, and gas can be stored and used at a human pace, with and lapses of attention are okay. For instance, I can step away from my stove for 15 minutes or half hour without burning the house down, and or I can leave a pile of coal for a few months, and it won't spontaneously burst into flame, much as I could leave a bucket of or a container of flour alone for a few months, and it wouldn't decay. It's forgiving. I can turn my car off even with a tank full of gasoline. I can leave it there for a month and come back, and my car will still be there. So that's a similarity to dry plant material. The fact that we don't have to pay that much attention to it, and it's portable, has a similar energy content. Okay, and I think that's a lot of why we use as much coal, oil, and gas as we do. Something that's somewhat, I would say it's more different. It's somewhat like, but not up there with being like. Okay, and so that when I say somewhat like, you should think, okay, well, this is a bit more different from the hunter-gatherer way of life, and therefore to be more poisonous, and therefore to make coal, oil, and gas harder for us to use. So somewhat like is is that coal, oil, and gas are basically non-toxic. They basically don't cause cancer, and we are therefore able to have a lot of these substances around us. So, like, I have gas piped directly into my kitchen, and I burn it. Um, and also I'm exposed to it in small amounts because it's there in my kitchen. Um, not tiny amounts, but small amounts. Um, or I'm able to wear clothing that's entirely made out of plastic, out of synthetic fibers, or uh, I can write with this pen that's made with plastic, and there's no problem, or not much of a problem. Certainly, we filled our lives with plastic, and the reason why we're able to do that is because it's relatively non-toxic, just like living just like plant materials. Um, but the reason why I say that coal, oil, and gas and plastics are only somewhat like is because there is some toxicity. Okay, so let's think particularly about plastics. Okay, some plastics are toxic. For instance, PVC, which is called vinyl, um, is often mixed with substances called phthalates. Okay, and the reason why you would mix vinyl with phthalates is because they make the vinyl less, they make it softer, less rigid, and less brittle, which you often want. Um, but the problem with phthalates is that they disrupt hormones. So if you get them into your bloodstream, they can mess up your hormones. Um, commonly, PVC is also mixed with lead. Okay, and for similar, lead gives vinyl flexibility and softness and brightness and durability. So, for instance, it's used in the artificial Christmas trees. The plastic needles in artificial chemistries might be 1% or more lead. Same thing with many children's toys. And uh, so if you have a plastic Christmas tree, you may find, if you were to measure the dust on your floor, you might find a lot of lead. Um, Another thing that there's a kind of plastic called polycarbonate, which um, commonly something is added to that called bisphenol A, or BPA for short, and it's a lot like estrogen, which is one of the principal sex hormones in the human body. It's a female sex hormone, and it controls the development of the female body, and it's used in polycarbonates because the combination of polycarbonate and BPA gives you a strong, hard, clear, shatter-resistant plastic. Okay, it's long-lasting, it's heat-resistant, so you can actually put it in boiling water to sterilize it, and it won't melt on you. So it's very useful. It gives you very nice bottles and kitchenware and all sorts of other substances. But you get that by putting in this BPA, which acts a lot like estrogen and can easily disrupt a male or a female's development. And in fact, over the last 50 years or so, there's been a large increase in male fertility, and in particular in the sperm count. So on average, the amount of sperm in a human male's semen is around half of what it was some decades ago. And people speculate about all sorts of reasons, and one of the reasons that they wonder about is whether it's because males are being exposed to a lot of BPA and phthalates. It could be. So that's it for the things that are somewhat like, in other words, in terms of being toxic, the coal, oil, and gas and plastic are somewhat like the fact that they have as little toxicity as they do is the reason why we're able to use so much of them, and why I'm able to eat my dinners off of plastic plates if I wish. But even there, it may be affecting worldwide fertility. So you wonder, is this really as close to the biosphere's way of doing things, to the hunter-gatherer lifestyle as it seems? Then we move up another stage towards the things that are a little bit like. There's still some similarity, but it starts to seem like it's more different than similar. Coal, oil, and gas are somewhat stable, okay, but you can leave a piece of wood just lying there for 10 years and it will never spontaneously burst into flame. It may rot slowly, very slowly, but it won't burst into flame. And same with other plant materials. But so that's what I mean by stable. It lasts and doesn't explode quickly. So coal, oil, and gas have some stability, but they're much more prone to explosion. Okay, even coal is prone to explosion. When you have a bin full of coal, there tends to be some coal dust, and the coal dust will fill the air around any air in that bin, and then a small spark can cause an explosion of the coal dust. But even much more explosive are oil and gas. Okay, and because they aren't that stable, they're storing and transporting coal, oil, and gas are much more expensive than storing and transporting plant material. So I think there's some similarity. They don't explode if you leave them alone for a second, but they are prone to it, and it makes our life a lot more difficult. Another thing that's a little like is the kind of smoke that's produced by coal, oil, and gas. Now, when we use in the hunter-gatherer lifestyle, the principal product of the things that we consume is the things that we exhale. Okay, and our exhalations are not poisonous. There's no risk to our life from the carbon dioxide and other things that we breathe out. Okay. On the other hand, the smoke from coal, oil, and gas is a weak poison. I'd say weak, okay, because it kills only some people and slowly. You might, if you breathe smoke a lot, then you may develop lung cancer later on in life, but it'll take you a while generally. Okay, but even though it's a fairly weak poison, it still is the smoke from coal, oil, and gas and things that we burn is still the third largest cause of death in the world. At least that's the estimates from the world's organizations like the UN and other large organizations like that, is that smoke causes around 7 million deaths per year. Many of those from COPD, where your lungs congeal. So it's a weak poison. It doesn't kill you very quickly, and it doesn't kill everybody, but by now it's killing an awful lot of people. So it's somewhat like the biosphere's way of doing things, which produces exhalations that are just not poisonous, but it's different enough that we're bearing a large cost. Another thing that, in fact, that's this sort of thing that's also part of why we don't like too much sulfur in our coal, is because, again, when you burn coal with sulfur in it, you get some interesting effects on the environment. Another thing that's a little like is that hunter-gatherers could go and do their hunting and gathering alone, or if they liked, in small groups. And coal also can be sometimes mined individually or in small teams. in the right circumstances, or there's an outcrop of coal on the surface, somebody can just go at the coal and or maybe go down 10 meters and go there and dig slightly underground. And just one person alone could do it, though in most cases that's not. Most of the coal isn't that close to the surface, but in some cases it could be, which is a little bit like hunting and gathering. On the other hand, most coal is a little harder to get at, and usually a coal mine will require hundreds of people. So not millions, but hundreds. So it's still a little bit like hunting and gathering, in that it's a relatively few people required to operate a coal mine, hundreds. On the other hand, nowadays, much of our coal and all of our gas and oil, well, I guess oil also, you can have these, just a single oil well, drilling an oil well, you need some expensive machinery to do it, but it's something that's, tens or hundreds of people drilling it and pumping out the oil. I'm not talking about the big things offshore, I'm talking about the small things in relatively accessible oil fields. But the fact is today, many of the coal, oil, and gas operations are huge. They require enormous machinery. Like coal fields that are 300 or 100 meters deep and have these huge machines that are absolutely colossal. So coal, oil, and gas are in a spectrum from, coal especially is sort of at the size, could on some occasions be at the same number of workers as a hunter-gatherer, one or two or a few, but more often they tend to edge upwards towards hundreds or thousands, and also to more and more large and expensive equipment. So in that way, they're a little bit like hunting and gathering, but they tend to edge away from it. Another one, here's one where I can show really clearly the spectrum of poisonousness. Okay, I can talk about three things that are poisonous to us and to the biosphere. And one of them is absolutely essential to the biosphere's functioning. Another one is part of the biosphere's function, not needed, but it's just around. So the biosphere has been everything in the biosphere has been exposed to it for millions and billions of years. And the third one didn't exist until we made it. Okay, and the first one, which is essential to the biosphere's function, we can produce an awful lot of it before it starts to have side effects that we worry about. The one that's just there but not needed, we can produce much less of it, and then the one that just didn't exist until we produced it, the amount that we can produce before it causes problems for us is just absolutely microscopic. So the three that I'm talking about are carbon dioxide and something called CFCs and lead. Okay, so let's talk about CFCs first. That's short for chlorofluorocarbon. They're commonly used as a gas inside of refrigerators and heat exchangers, and they're convenient for that purpose. They don't burn, so they're not a fire risk if they escape from the refrigerator. And so they were heavily used, particularly between 1970 and 1990. During that period, the world produced enough of them to make a total of 2.5 kilograms of CFCs per person around the world. And so, and shortly after 1990, we tried to end our production of CFCs. And so probably the total produced worldwide is somewhere more like 4 kilograms per person. And the reason why we after 1990 tried to stop producing CFCs was because we discovered an ozone hole over the poles, especially the South Pole, and in fact, if we'd produced a little bit more CFCs, maybe 10 kilograms would have been enough, the ozone in the sky would have disappeared all over the planet. And with no ozone, there would have been a lot more UV radiation everywhere, and everyone would have been getting terrible sunburns every time we went outdoors for even a few minutes, not to mention all the livestock and all the plants getting sunburns. It would have been enormously destructive. It would have been a lot harder to do anything outdoors, or for the biosphere to live. It would have been a tremendous hardship. And so 4 kilos was enough to put us right on the edge of that kind of catastrophe. It wouldn't have been a catastrophe for the biosphere. I'm sure it would have adjusted. It would have been difficult for things in the biosphere, but it would have been catastrophic for us and for our cattle. Actually, I should note that we are still producing CFCs. We're producing them at a little more than 1/10 of the rate that we were during that period, and it's not publicly known who's doing it. Maybe some corporations in China could be, but it's not clear exactly who's doing it. And it would be very easy if worldwide regulation broke down for people all over the world to restart the production of CFCs, and we could be right back to where we were in 1990. So that's an extremely poisonous substance, and it's not a coincidence that it's just very far from the there weren't CFCs in the world before we produced them, and that's the reason why they're so poisonous. Now let's move a step towards more common. Okay, and this is a substance that was present everywhere, but nothing in the biosphere really needs it. Okay, but it was present, so everything in the biosphere had to learn to live with small quantities of it, and that substance is lead. And at this point today, we're producing around 2/3 of a kilo per year per person, and by now we've probably mined and produced at least 100 kilos per person. And it's not something that decays; it's an element. So once you mine it and produce it, it's here forever. And so this is 100 kilos per person, a lot more than the 2.5 or perhaps 4 kilos of CFCs that we've produced. Okay, but we aren't anywhere close to generating an ozone hole or something like that. However, even though it's relatively weak effects, it's estimated that the lead that we have released into the environment is causing about 1 million deaths per year. And then in addition to that, even more people with severe intellectual disability, and also even among normal people who aren't so profoundly affected, it causes a nationwide decrease in IQ and loss of emotional control. So it's estimated that, like in the United States, the average United States citizen's IQ score is maybe 2 points or 3 points lower than it would be if we had never used lead. So that's something that was present in the biosphere in some quantities, so we're more able to tolerate it, but it still has its effects. Okay. So, and then the last one, this is something that is absolutely essential to the biosphere, so it's only extremely weakly poisonous. It's carbon dioxide. Okay. And in fact, every time you breathe out, you're producing carbon dioxide. Everything that the biosphere does, everything that every animal or every bacterium does produces carbon dioxide, and then that carbon dioxide is used by the plants to make plant material. So it's necessary, and for that reason, it's every living being has to deal with carbon dioxide, and in fact needs carbon dioxide, and so it's only very weakly poisonous. It's like it's poisonous in the same way that water is poisonous. You need it, but if you're suddenly immersed in a huge in water and can't get a breath of air, then you die. Same same sort of concept. So far, remember that so far we've produced maybe 4 kilos of CFCs, and that was enough. And for us to say, let's stop. We've produced 100 kilos of lead, and we're still producing. And with carbon dioxide, we're producing around 4,800 kilos per person per year. So 1,000 times more than the CFCs, and 100 times, also 1,000 times more per year than lead. Okay, and in fact, our fires produce 20 times more carbon dioxide than what we breathe out from the food that we eat. Okay, and so far we've increased the atmosphere's concentration of carbon dioxide by 50%. It's 1.5 times more than it used to be. Okay, but it's only now that we're beginning to think that perhaps we're starting to see real environmental effects from this large increase in carbon dioxide. So this is something, so things that are close to the biosphere's way of doing things, like carbon dioxide, are only very weakly poisonous, so we can produce a lot, we can use them a lot more. Things that are very far from the biosphere's way of doing things, like CFCs, are much more poisonous, so we can only use a tiny bit of them. So that's the trade-off that I'm emphasizing here. Okay, overall carbon dioxide is still a poison, but it's a very weak poison. Okay, so it's a little like if we were producing small quantities of it, if we were using much less energy, I'd say it's like the hunter-gatherer way of doing things, but the fact that we're using 20 times more per person, it means that we've sort of, I'd say at this point it's a little like the hunter-gatherer way of doing things because we're using so much of it. Then there's several things that are just unlike the biosphere's way of doing things. Okay, one of them is that every stage in our use of coal, oil, and gas requires a lot of machinery and infrastructure. Getting it out of the ground, storing it, processing it, moving it to where you are, using it in the way that you like. You know, we need roads, we need parking lots, we need machines. In fact, most of the world's roads, parking lots, and machines are here simply because we're accommodating ourselves to what you have to do to use coal, oil, and gas. We wouldn't, if we got most of our energy from crops, it wouldn't be the same. We wouldn't need so much of these things. Like parking lots, wouldn't need so many parking lots. Another thing that's completely unlike is that coal, oil, and gas are not nutritious. They're no good for eating. Another one is that they are, if you breathe gasoline or natural gas, they can hurt you very badly. Or if you drink gasoline, it can kill you. Another thing that's unlike is that it's very difficult to use them for anything except for fire. The world's plants and crops and trees and so on have all sorts of uses. Coal, oil, and gas are just good for fire. Or for making plastic, yes. But even that was very difficult. It took us, between when we started really burning oil a lot for our cars and vehicles around 1910, until when plastic was invented around 1950, that was a 40-year lag. And the people who figured out how to do it, how to make good plastic, there was some plastic efforts earlier, but that wasn't useful. The first useful plastics were invented around 1950 by Natta and Ziegler, and they very, very quickly got a Nobel Prize because everyone knew this was a stunning achievement. It was really hard to do. And even now, you take crude oil, you refine it in a huge oil refinery, then you take some of the products, put them in a factory. The factory's job is to turn these oil products into plastic resins, and then later and maybe mix them with things like lead or BPA or whatever, and then you take the result, those resins, and you take them to another factory where you manufacture the plastic things. Okay, it's still a very complicated, intricate process. It's much different from cutting down a tree and having something you could make a piece of furniture out of, or cutting some plants and weaving them into a basket. Okay. Another thing that's completely unlike the biosphere is that the one thing that, as I said, coal, oil, and gas are mostly good just for burning, but you can produce plastic. Plastic is completely unlike the biosphere's products in that it doesn't really allow maintenance or repair or repurposing. It's unusable by the biosphere, and it's basically unusable to us after we're done with its first use. Very small, for all our recycling efforts all over the world, only a very small percentage of the plastic that we produce is actually reused. A lot of it is burnt or thrown in landfills. And then of the plastic that is reused, it's almost none is reused a second time. The more times you reuse it, the less lower quality it is. Okay, so we're almost there. There's one more immense difference between coal, oil, and gas in living plants, and I just want to put it very baldly. They're anti-democratic. They concentrate power in the hands of a few. A society that depends on coal, oil, and gas gravitates towards having all of its power concentrated in the hands of a few people. So in theory, if you get your energy from the land, either from hunting and gathering or from farming, then at least in principle, individual people can be responsible for individual pieces of land, and so you can have kind of a land democracy. It's not exactly the same as every person having a vote, but every piece of land, in a sense, would have a vote, and the people on it would have their vote. Because cropland punishes landowners in societies if the individuals on the land are not given respect and responsibility for the land and liberty and independence and personal reward. We saw that in the episodes about how to get the best from the world's land. To get the best from the land and to make sure it doesn't degrade and become unusable, you really need to give it a lot of personal attention. And the way to give it personal attention is to have people living on the land who care about it and have a reason for caring about it. They're rewarded for when it does well. They have a personal responsibility and decision-making power about that land, and they're respected for it. They're kept safe and so on. When you do that, when a society does that, it'll get the best from its land. If it doesn't, it'll be punished. And it'll be punished because the land will give a poor harvest and it will degrade until it has to be left unused. So if in a world that gets a lot of its energy from land, the land will earn the people working on it some kind of voting right, some power, because the society will depend on each person, on the people's attention to that land and their work on that land, their intimate knowledge of the land. So there's, you may have heard of the phrase sweat equity. It's a real thing with land. Okay, if you work it, you have some kind of right. And so there's a pressure for some sort of a democracy among land workers. I'm not saying it's exact modern democracy, but it is something where each person has to be given a say in determining what's going on their land and the things that are pertinent to their affairs on that land. And if each person working the land isn't given their say, the society as a whole will suffer. In contrast, coal, oil, and gas are completely different. They're only on some land, only some certain small portions of the land have coal, oil, and gas, and those portions of the land are owned by only a few people. And in general, you can only get the coal, oil, and gas with a large amount of equipment and money. So there's no way to produce a democratic arrangement here. Only a few people will possess the coal, oil, and gas, and and the money and the equipment required to get it. And almost everyone will be reduced to basically helpless dependence, somehow having to bargain every day for some energy, begging or bargaining. So, in fact, that's where we are now. The production of coal, oil, and gas is in the hands of a few, and most of the world is in the position of depending on those few, and have to arrange in some way to make sure that those few keep giving us coal, oil, and gas. And you have to wonder, in this situation where a few have the keys to the society, how long a real democracy can last, and how real our democracy is today. It's certainly a very awkward and unstable position, and you can't expect it to go on. If it is democratic today, you can't expect this arrangement to go on forever. If a few really do have all the playing cards, then sooner or later they'll exercise them. So that's it for today. I've gone over I've gone over poisoning. I've gone over the natural way for us to get our needs fulfilled, which is living as hunter-gatherers, and that's the way the biosphere is set up, and the way that we're set up. And then I talked about the poisoning effects that we undergo by moving to a farming and pasturing lifestyle, and they are there, and they are substantial. And then I talked about the side effects when we move from a farming and pasturing lifestyle towards a coal, oil, and gas lifestyle, which is where we are now. We get around 3 times more energy from coal, oil, and gas than we get from our farms and pastures and forests. And then next week I'll be talking about the cost of the poisoning effects of using renewables and coming to depend mostly on electricity, renewables and nuclear. So that's the last degree of separation. It's the most unlike the biosphere's way of doing things, and you'll find that the list of differences and side effects is large, even compared to coal, oil, and gas. So, and that's the basic reason why we'll never build more than 15,000 calories of renewables and nuclear per person. Just too many side effects, too poisonous, too hard to endure. So we're almost there, and we're very close to ending this first of the 3 stages of this channel, where I'm talking about our exponential growth, as I have been, and how much energy we'll be able to get long term. So in a few episodes we'll be winding this up, maybe 2 more episodes, and then we'll be moving into the second stage, which is about where the human race stands right now, where we are in the process of the end of the exponential growth, and what's going on right now. And then the last stage will be the future and how to prepare for it. So with that, I thank you for your attention. If you know anybody who may be interested in this, please invite them, and keep coming back.